The time has come, the walrus said, to speak of many things. Well, actually just one thing. We got to put a power cord in this unit, and if you'll notice back here there is a spot where the cord goes through. Then what we're going to be doing is tying a knot on this side. So let me do that to start with. Okay, it's fed through, and then what we're going to be doing is tying a knot. And the way that I do this is I tie one loop like that, and then I bring a second loop around and under this part. So in other words, I go right through here. And I do that so that I have found by doing this double loop, the cord does not pull out of the when you put pressure on this, the cord doesn't unwind itself and slowly slide out of the radio. There are lots of ways to do this, and so I'm not advocating that any particular way works. There are little clamps you can buy to put on it and other things, but basically that's the way I'm going to do it. So the next thing I'm going to do is determine which of these two wires is the neutral, because that's the one that we want to connect down here to the switch. So I have one end of the multimeter, one lead, clipped to the neutral. Remember, that's the wider spade. Well, my probe just slipped out of the banana or the alligator clip. There we go. And then I'm going to go over here, and I've got it set to beep for me. That's the neutral. So that's the one that's going to go right here to the power switch. Let me solder that on. Okay, I've soldered that to the power switch, and now I'm going to connect the other end of this to the ground or to the hot side of the chassis. Remember in the schematic that one side of the power lead, the neutral, goes to the on-off switch and to B-, and the other side is going to go through a 1/2 amp fuse. So let's talk about fuses. At the top are an assortment of what today are called 30 millimeter fuses. They used to call these 3AG and other types. And that contrasts with the smaller 20 millimeter fuses. Notice the difference in length for these, and also in diameter. When you're buying fuses, make sure that you get the right size for the holder. Now, fuse holders come in a variety of types. This is one type that I like to use. It has a hole in the center. You can drill a hole in the chassis and mount it straight to a metal chassis. The covers here provide some protection, though it can still be dangerous to make contact here. That's why you never want to mount these on top of the chassis. You always want to mount them underneath, where they're you have to at least remove some screws to take the chassis out. This is the kind I prefer because it's easier to check and change the fuse in these. But there are lots of other kinds. This is a 20 millimeter and this is a 30 millimeter size of a fuse socket that unscrews, and you see the fuses in there, and then you just screw it down. Same with this one for the 30 millimeter sizes. But what we are actually going to use is what's called a pigtail. Pigtail because it just has a little piece of wire on each end like this, and the fuse is in the middle. This once again unscrews. I won't unscrew it. I'm going to start out with an 8 amp fuse. Now, obviously you don't want to leave an 8 amp fuse in the circuit, but of course an 8 amp fuse simulates just a straight wire, which is the way the radio has worked for the last 60 years or so. So with an 8 amp fuse in, I'll be able to measure the current that the set uses, and then I'll determine the appropriate size fuse. I think it's going to be a 1/2 amp, but it could be a little different. Now we have the multimeter, the ohms setting of the multimeter connected across the AC line, and I'm going to turn the switch on and measure the resistance. Okay, 119.5 ohms. That's about right. If you remember from an earlier video, I said you get about 1 ohm per volt on the AC, these AC-DC sets, these 5-tube radios. The filament string, each ohm of filament resistance, cold that is, represents approximately 1 volt voltage drop. So 119 means that this is approximately a 119 or 20 volt, 120 volt filament string. So that is promising. Now we are about to go into a phase where there is some danger. So be aware when you start plugging in any pieces of equipment, especially equipment that's exposed like this, you need to be sure you know what you're doing. So if you don't have a mentor and you don't know very much about electricity and don't understand the safety rules, don't try this yourself. Get someone to help you the first few times that you work on electronic equipment that is actually connected to the AC line. Eventually you'll develop enough skill and knowledge that you can do it safely yourself, but in the beginning it's always better to have somebody watching over your shoulder and helping all along the way. Don't depend on the internet or YouTube to teach you these things. I suggest you get an actual teacher. If you don't have one, see if you can find somebody through a local ham club or through a local community college or somebody who is willing to be your mentor. It'll make things a whole lot safer. Now I've plugged the cord into this variable isolation transformer. Now, these are, as things go, relatively expensive, quite a bit more expensive than the multimeter we've been using. But they are a really good safety device, and they also have some other features that you might find worthwhile. So if you can afford one, I would get this set up. Now there are other alternatives, and if you understand them, they are equally good, or at least equally useful. Things like dim bulb testers and other techniques. But we're going to use this. What we're going to do is we're going to turn this on. We're then going to turn the radio on. You'll just hear a click. And now I'm going to start raising the voltage. And this unit is set to read current. Watch the needle. I'm going to keep coming up until I reach 120 volts. Now, let's take a look down here at the radio. Especially pay attention to the pilot light. And I hope this will show up on the video. As the filaments warm up and the tubes start drawing current, remember, we'll come back and look at this on the schematic in a second. The sum of the current that flows through all of the tubes, that is the rectified B+, flows through this pilot light. And you may notice it's getting brighter. That is a good indication of two things. One, obviously that the bulb is good, but also that your rectifier tube, the 35Z5, is conducting current. Let's take one more look at that on the schematic. I've turned the power off, by the way, for those of you that were wondering, and you should have been wondering, because I've turned the power off to the unit, because I never put my hands near a unit like this with power on unless I have to do that. In other words, I need to be able to make some measurements with the power on. You may remember that we talked about the fact that the current that flows in through the hot lead of the AC line flows through this dial lamp and also through this part of the 35Z5 filament. Those are in parallel, and that current comes to the plate of the 35Z5, and that is the source of all of the B+ that is used in the set. That's why, when you first turn the power on, these filaments begin to get warm, and they begin to glow an orange glow. The dial lamp comes on at kind of a medium to medium-low brightness. Then, as the 35Z5 begins to conduct, and as the other tubes begin to conduct, the current through the 35Z5 goes up, and the dial lamp handles some of that current, so it goes up as well. It's a neat way to watch whether the set is coming up as you expect it to do. Okay, now the next thing we're going to do is we're going to measure some voltages. Before we measure voltages, I forgot that we need to determine how much current that this set is drawing so we can properly size the fuse. So let's come up here and let's look at the meter on this Syncor PR57. You probably will have trouble reading that. Let me reset the camera. Okay. This scale, the one right here, the top numbers indicate the wattage and the bottom numbers the current. This is drawing about 0.25 amps, and it's consuming just under 25 watts. Remember, we said it was a 30-watt unit. Now, the 30 watts would be with the volume turned up, which we have the volume turned down now. There also are other ways, other instruments that you can use to do the same thing. This is another Syncor instrument. I'm going to turn this off. Another Syncor instrument from the past. It's called a Fuse Safe. Zoom it just a little bit. And it also would do the same thing. That is, try to get the meter to show. It indicates, and it actually has a little scale on it that shows you may not be able to read it, that shows a 1/4 amp, a 1/2 amp, a 3/4 amp, and a 1 amp fuse, and so on. These are not very easy to find these days. They were fairly popular back in the day. One of the things that you can find are these power line monitors. This particular one, it has the brand name Kilowatt, and it plugs in to standard 3-wire, and then you plug the unit in here, and then you read various things here, including the amperage and the wattage. You push a button for amperage, push a button for wattage. I may show this a little later, but I mainly wanted to refer to it for those of you that might be looking for another way to measure these things. But the third way is to properly use, and here you need to know what you're doing, the amperage measurement capabilities of your multimeter. Now, most multimeters that will measure AC current will measure up to 10 amps. I suggest you start with the 10 amp setting, and you'll have to read your instruction manual to know how to use your particular meter. But you can use this meter to determine how much AC current this device is using. And The one trick that radio repairmen back in the day used to use to do that is if you measure across, if you turn the unit off, hook the power cord to an AC line, and then put your meter, being very careful not to short the leads together, but put your ammeter, your AC ammeter, make sure it will read alternating current ammeter, has that setting and that you're using it properly. If you then put the two leads across here, it will tell you how much current this set is using. Always start with the highest amperage range you have on your meter and go down until you get the accurate reading. So, with that in mind, I'm going to now replace the fuse that, by the way, I don't know if I ever showed it to you, but it's right here. And this is, I put some heat shrink tubing on this end, and then I brought the other end down here to pin 2 of the 35Z5. So I'm now going to replace this with a 1/2 amp fuse. Okay, I've installed a 1/2 amp fuse, and I've now powered the radio up and turned the isolation variable isolation transformer up to 120 volts. Now what I'm going to do is turn the power off and right back on to see that the fuse handles the surge current. Now, why did I do that right away? Why didn't I wait? Well, this set draws the maximum current when the filaments are hot and all of the tubes are conducting. You can tell that, and one of the reasons I pointed out earlier, that when this dial lamp is at its maximum brightness, that's when the set is drawing the most current. So that's where you want to test for surge. So we turn it off and right back on, and the set should come back on without blowing the fuse. Now, we know that if we draw more than 1/2 amp, that fuse is going to blow. So it is very likely that the fuse will be the first thing to go. I say likely because I have seen sets with properly sized fuses before where some unique situation has happened that causes something to burn up even though it had a properly sized fuse in it. But in general, a good properly sized fuse is the biggest safeguard, and in my opinion the best, against the radio going up in smoke someday. Okay, enough of that, and I hope at this point you realize that safety first, then have fun. And in that regard, let's now move on to measuring the voltages in this set. Well, I'm set up to start measuring voltages, and what I'm going to be doing is, just as with resistances, I'm going to be filling out this chart with the voltages. Now, of course, some of the voltages will be AC and some will be DC, and so I'll be going back and forth on those. I'm going to be trying to use this box that I built, this set tester, but I will tell you that one of the problems that this is going to have is with these long wires. When I try to use it in the RF sections, that is the mixer converter and the IF amplifier, it's going to cause problems because of all the stray capacity and feedback and other things. So I kind of know that ahead of time, but I should still be able to measure some of the basic things, the DC voltages, the filament voltages, and so on, even in those tubes. Then in the 12SQ7, the 50L6, and the 35Z5, which is where I'm going to start, I should be able to measure the AC and DC voltages there. So I'll come back in a second with those values. Okay, well, here are the values that I got for all of the various points. Now, some of these where it says 0, it might have been a couple of millivolts, and so on, as I expected. When trying to work in the 12S-A7, that's the mixer oscillator, and in the 12S-K7, many of the signal lines were causing problems. For example, when I was using the 12S-A7 with the set tester literally kills the converter. And by kills, what I mean is it stops the oscillator from working, so it doesn't convert any of the RF signals to IF signals without an oscillator. Similarly, when I tried to use it with the 12S-K7, it caused the 12S-K7 to oscillate, and which of course produced a heterodyne. I won't get into all the details. At any rate, it caused the SK7 to be unstable. So some of these readings I had to take by using either going underneath or by using one of these type adapters, which of course have much shorter lead lengths from added to the circuit. So what I'm going to be doing now is looking these numbers over. I'm also going to be comparing them to a list I found out of the book All-American 5 by Ray McWhorter, or Richard McWhorter, I'm sorry, this book. In the back of that is this chart. So I'm going to be comparing his voltages to my voltages. There are some things where there will be differences, and I should have mentioned this maybe earlier in the set of videos. Sometimes tube pins are used as tie points where they're not used inside the tube. So occasionally you'll run across a voltage on a tube and you'll say, how in the world did that get there? Well, it's because you're actually measuring the voltage of a point in the circuit that's not actually connected inside the tube. It just is being used as a convenient tie point. So I think at this point I'm going to wrap up this video and analyze these results, look them over with regard to the schematic and the All-American 5 data that I found. And then in the next video, we'll come back with conclusions, and maybe we'll be able to start doing some alignment. In the meantime, have a nice day.